There's one last thing we're going to take a look at in section 1.3, and this is an important theorem called the squeeze theorem that will show up from time to time when we try to deal with certain types of limits. Let's take some function f of x, and I want to find the limit as x approaches c. And let's pretend I don't really know what this looks like, but I'm going to have a little bit more information about this function. Particularly that at x equals c, it's going to get squeezed in between two other functions. So let's say I have some function over here, g of x, and let's say I have some other function above it that I'm going to call h of x. And the idea is going to be, let's say I don't know how to find the limit as x approaches c of that function f of x. But if I can find the limit as x approaches c of g of x and of h of x, and they're both getting close to that same value, they're getting squeezed into the same value, well, that's going to be the same as the limit of my function. Let me actually write this out and be a little bit clearer about this. First of all, if around x equals c, I have g of x less than or equal to f of x, less than or equal to h of x. So in some region right around x equals c, I know that g is on the bottom, followed by f, followed by h. If that's the case, then the limit as x approaches c of g of x also has to be less than or equal to the limit as x approaches c of f of x, which is also going to be less than or equal to the limit as x approaches c of h of x. We're actually going to use this in a moment to try to prove our first special trig limit. The second special trig limit will follow from a similar argument. But before we do that, let me try to show you an example of a way that I guess this problem could sort of be tested. This came from the College Board from their AP classroom. Let's take a look at a couple functions here. Let's say g of x is the function, the sine of pi over 2x plus 4. And let's say that h of x is some function, let's make this a polynomial, negative 1/4 x cubed plus 3/4 x plus 9 halves. If we know that g of x is less than or equal to f of x, which is less than or equal to h of x, let's say between negative 1 and 2, what is the limit as x approaches 1 of f of x? We know nothing about that function f of x other than the fact that between negative 1 and 2, that function f of x is in between g of x and h of x. So, by the squeeze theorem, I can set up the following inequality. I'm going to write out by the squeeze theorem. No, I don't necessarily think you have to say that, at least for right now. By the squeeze theorem, I know for a fact that the limit as x approaches 1 of g of x is less than or equal to the limit as x approaches 1 of f of x, which is less than or equal to the limit as x approaches 1 of h of x. As far as this limit goes, well, I can just go and plug into that thing. So I'm going to get the sine of pi over 2 plus 4. Don't know anything about that, so let me just copy over that limit again. I'm going to say the limit as x approaches 1 of f of x less than or equal to. Well, this limit over here, I'm going to plug 1 into my h function, and I'm going to get negative 1/4 plus 3/4 plus 9 halves. Let me do some simplifying here. I know that the sine of pi over 2 is 1, so 1 plus 4 is 5. 5 is less than or equal to the limit as x approaches 1 of f of x less than or equal to. Okay, so negative 1/4 plus 3/4 is 2/4. Let's call that 1/2. A half plus 9 halves is 10 halves. That's 5. I don't know what this limit is, but I know it's got to be in between 5 and 5. Well, there's only one number in between 5, and that number has to be 5. And this is usually how our squeeze theorem is going to work. If I know that this number and this number are the same thing, that's got to be the same as the number for the limit in the middle. Let me see if I can show you a PowerPoint that will go through how we can use our squeeze theorem to prove our first special trig limits. So we're going to take a look at why the limit as x approaches 0 of sine x over x equals 1. I wouldn't bother taking notes on this, just watch, follow along, and see what's going on with this. The proof for the other special trig limit follows from a similar argument. The first thing I'm going to do is I'm going to start with a wedge of the unit circle. Here's my unit circle, so my radius is 1, and this distance over here has to be 1 because it's the same radius. If I'm going out horizontally, this point over here has to be 1, 0. And this point over here on the unit circle is, well, the whole point of it being the unit circle for trig, is the point cosine theta, sine theta. Next is I'm going to draw in a right triangle circumscribed about the wedge. So I've got that triangle, I'm just going to extend it and then come down over here. What I need to do is I need to find the coordinates of this point over here. X coordinate, I think, should be really easy. I think the x coordinate is just going to be 1. The y coordinate is going to take a little bit of work. First thing we're going to do, we're going to notice that the coordinates over here are my origin. I'm going to call those coordinates 0, 0. And I'm going to try to write the equation of the line for this hypotenuse of the right triangle. And I figure if I can get the equation of the line, then I can just plug in 1 for my x and figure out the y coordinate of this point. Well, equation of the line, I'm going to use y equals mx plus b here. I'm going to find my slope. My rise is, let's see, sine theta minus 0, and my run is cosine theta minus 0, just sine theta over cosine theta, or really just tan theta. Okay. My y-intercept, again, is just 0 because this point over here is 0, 0. My slope is the tangent of theta, so my equation, I realize this looks weird because there's 3 variables, just go with me on this. The equation of my line is y equals the tangent of theta times x. What I want to figure out the y coordinate over here. Again, if my x coordinate is 1, I'm going to plug in a 1 to that equation. Y equals the tangent of theta times 1, tangent of theta. I realize there's a lot of thetas in here, but stick with me on this. The coordinates of that point are 1, the tangent of theta. I'm also going to draw in an altitude from this point straight down, so I've made another right triangle over here. And the point is, I now have 3 shapes. That small right triangle, the wedge that I was starting with, and the bigger right triangle. And I want to compare their areas. And I hope you can look at this right away and know that this area has to be the smallest, followed by this one, followed by this one. I'm also sure you're probably wondering, what on earth does this have to do with that first special trig limit? Just keep watching. I now want to go and I want to find the area of each of these things. Okay, well, this triangle over here, the base of my triangle is, well, just the x-coordinate of this point. It's the cosine of theta. The height of this triangle is the y-coordinate. They're the sine of theta. So the area of that triangle is 1/2 base times height, or 1/2 times cosine theta times sine theta. As for the area of a wedge, well, a wedge is just like a fraction of an entire circle. I know the area of a circle is pi r squared. What fraction of a circle is this? Well, whatever that angle is divided by an entire circle. Radians here, so I'm going to say times theta over 2 pi. Okay, so what's the radius of this wedge of a circle, the sector of a circle? It's 1. The angle, I don't know, I'm just going to call it theta, so times theta over 2 pi. Simplify this, and you're going to get an area of that thing to be theta over 2. Finally, this triangle over here, my base is 1, my height is, well, just the y-coordinate of the point over there, tan theta. So I'm going to say a half times 1 times tan theta. I'm going to get tan theta over 2. Again, I hope you realize that this area is less than or equal to this area, less than or equal to that area. So I can set up this three-part inequality. Get rid of the a's, and I'm going to say sine theta cosine theta over 2 less than or equal to theta over 2 less than or equal to tan theta. And I'm going to work through some algebra stuff here. First of all, there is no need for us to have the over 2's. How about I just multiply all by 2? So I'm going to get sine theta cosine theta less than or equal to theta less than or equal to tangent of theta. Then I'm never a fan of tangents. I'm going to rewrite my tangent in terms of sines and cosines. So I'm going to say that that's sine theta over cosine theta. Then I'm going to divide all three parts by the sine of theta. Again, don't worry too much about trying to figure out where this is going. Just follow what I'm doing. Divide by the sine of theta, divide by the sine theta. When you divide this by the sine of theta, you get, well, that sine theta is gone, so 1 over the cosine of theta. Next thing I'm going to do, I'm going to take the reciprocal of all three parts. Reciprocal of cosine theta is 1 over cosine theta. Reciprocal of the middle is sine theta over theta. Reciprocal of 1 over cosine theta is the cosine of theta. But when I do that, I change the direction of the symbols. And why would this happen? Well, let's take a look at this really simple inequality. 2 is less than 3 less than 4. If you take the reciprocal, you've got a half, a third, a fourth. Well, a half now is the biggest one, followed by a third, followed by a fourth. Hopefully that might be enough to convince you why, if we take the reciprocal, we have to change our symbols. Well, let me put some limits over here. Let me take the limit as theta approaches 0 of all three of these pieces. And then let me go and find the limit. The limit in the middle, well, that is my special trig limit that I'm trying to prove is 0. But this limit over here, the one on the left, you're going to go plug 0 in for theta. You're going to get 1 over the cosine of 0. Cosine of 0 is 1. 1 over 1 is 1. Plug in 0 over here. I guess I already did that. Cosine of 0 is 1. Both of those are going to be 1. I'm using my squeeze theorem here. What number gets squeezed in between 1 and 1? It has to be. That theorem, that special trig limit can be proved using our squeeze theorem.